this up in case people don't make it. Beautiful. Good morning, everybody. We are going to take a look at section 6.2 today. It's called confidence intervals. And this is a little bit more realistic situation. We're going to estimate the mean of a population when the standard deviation of the population is unknown. So if you'll remember back in section 6.1, we estimated the mean given that we actually knew the standard deviation of the population. And that seems like it wouldn't happen very often because how would we know the spread of a population if we didn't know what it was centered around, right? So it seems like a fairly unlikely situation where we would not know the mean, but we would know the standard deviation, and then we want to estimate the mean. And the fact of the matter is that just doesn't happen very often. So 6.2 is the more realistic case. The reason we did 6.1 first is because it's a little bit easier to get sort of your head wrapped around, and then we'll talk about how they differ, right, in section 6.2 today. That's our plan. You guys have any questions for me before we get started?
No, I don't think so.
Okay, well, stop me if I get going too fast. Jason, what can I do for you?
No, I'm good. I didn't have any questions.
Okay, make sure you slow me down if I go too fast, and we can certainly take a look at some of your questions from the homework if you have some, either later on today or in office hours or as we go on down the road. Okay, so here's the warm-up. And essentially, this is what the whole chapter is about. We would like to estimate some population parameter, right? In this case, the mean, using a sample. So in this particular problem, we're going to estimate the average age of college students. And so to do that, we're going to take a random sample and take a look at the mean of our random sample and use that mean as a point estimate. So they went ahead and did that. They did a sample of size 20, and then they added up all the values they got, divided by 20, and got a sample mean of 22.9. So as a point estimate, you could say, well, I think all college students are going to have an average age of about 22.9, based on my one sample of size 20. And you say, well, okay, that's great, but it was only one sample. There's probably, if we were to talk about our college, there's 20,000 college students if you count all the part-timers. A sample of size 20 would give us an idea of how old they are, but it doesn't really make me feel too confident that we've got this down exactly right. Meaning that, it's possible that if I took a sample of size 20 from GCC, that those 20 people could, all be over 50. It would be unlikely because our average is probably somewhere a little higher than 23. It's probably more like 25. But certainly there are 20 people at GCC that are over 50. And so if you were just picking a random sample, it would be unlikely that you would get all of them over 50, but it is possible, in which case your sample wouldn't be very representative of the population as a whole, and your mean wouldn't be a very good estimate. Likewise, there are certainly 20 people that are 15 years old or younger, right? So we have some running start type students at GCC, and it's possible that you could get a sample that had all 20 of them being under 15 years old, which again wouldn't represent the population. But if you were to take lots and lots of samples, you would expect some older students, some younger students, but most of the students, somewhere around, scattered around the average age of, for us, maybe more like 25, and in this particular problem, somewhere around 23. Good so far?
Yeah.
Okay.
Yep.
We're going to make an assumption, though, and that is that the ages of college students are scattered around the mean. In other words, most of them are about the average age, and then there are a few younger ones and a few older ones. This assumption is that the population, the whole population, all the ages of the college students are normally distributed. So when we say the population is normally distributed, we're saying, you know what, it's not like we just have either 15-year-olds or 50-year-olds and nothing in between. We're saying that really it's bell-shaped and symmetric about the mean. And so this assumption that if we took a sample, we should get students whose ages are somewhere around the mean seems reasonable. Okay. And for ages of college students, that's a reasonable assumption that they are normally distributed. If we're trying to do a confidence interval for a different data set that's not normally distributed, then it's going to be important that we pick a sample size that's a little bit bigger. In fact, our cutoff is generally 30 or more. So here's what we know. We know the standard deviation of the population. So what we're saying is, I don't know how old they are on the average, but I know their ages vary by about 1.5 years. Again, this is an extremely unlikely situation because if you don't know the mean, you probably don't know the standard deviation either. And that's what we're going to talk about today in 6.2 after we get done this example. So we would like a 90% confidence interval. And so a confidence interval is going to say not just the average age is 22.9, but we're going to say plus or minus how much, right? We're going to give a margin of error around our estimate. And we would like to be 90% confident, meaning that we would like 90% of the sample means, okay, to fall in this range, this confidence interval range. So here's what we're going to do. We have two distributions that we're going to look at. First, we have the distribution of all college students' ages. So these are the ages of students. The problem told us that we know that they're normally distributed, or we could make that assumption, and I think that that's reasonable. They're going to be normally distributed around some population mean. And we don't know what it is. That's the point. We're trying to estimate it. But we do know that the spread, right, that the spread of this population is about 1.5 years. So 68% of the college students are going to be either up 1 standard deviation or down 1, between -1 and 1 standard deviations, or in about a 3-year window. And then if we go out here, 2 standard deviations, 3 standard deviations, by the time we get out to 3 standard deviations, right, we know from the empirical rule that 99% of all students are going to be in that range. So 3 times 1.5 is about 4.5. So 2 4.5s is about 9. So in that 9-year window, we're going to expect almost all of the college students. All right, and that was information back from normal distributions, which I think was what, the beginning of chapter maybe 4, the end of chapter 4, and the beginning of chapter 5. So now what we want to do is we want to take a sample. So we take a sample of size 20, and we get an average age of 22.9. And so we want to say, how weird is this average of 22.9, based on a sample of size 20? So what you would look at is the distribution of all possible samples. So you'd take a sample of size 20 and a sample of size 20 and a sample of size 20, and you'd calculate all the means, and then you would look at the histogram. And so we would get a histogram that looks something like this. This would be the distribution of the sample means. Okay, so we've got one sample mean, And we would like to know, what does the distribution of all those sample means look like? So according to the central limit theorem, it's going to say it's going to be normally distributed, okay, and less spread out than the population itself. In fact, we know where it's centered and how spread it is. The mean, right, the mean of the sample means is going to be centered at the mean. In other words, the average of all the averages is going to be the average. But the standard deviation of the distribution of sample means is going to be the standard deviation of the population divided by the square root of the sample size. Basically, this says as the sample gets bigger, our estimate gets better, right? Because there's less spread. And so if we're going to calculate this spread, then we need to know sigma. In other words, we need to know the population standard deviation, so we can plug it in right here. And in this problem, we do. However, in section 6.2, we don't, and we'll deal with that when we get there. So I'm plugging it in. The mean is what we're trying to estimate, right? So we don't know. But the spread is 1.5 divided by the square root. Our sample size was 20. And so trying it on the calculator, I get 1.5 divided by square root of 20, or about 0.34. So about a third of a year, 4 months or so. Notice that the ages are spread out by about a standard deviation of about 1.5 years, but samples of size 20 are only spread out by about 0.34 years. So that goes over to here, right? Here's our spread. Okay, so we want to know what's a 90% confidence interval for this 22.9? So we're saying, where would 22.9 fall most likely in this distribution? And so maybe it's a little above the mean, a little below the mean, but the chance it's way out here, several standard deviations away from the mean, is extremely unlikely since there's not much area left. Okay, so we want a 90% confidence interval. To find one, we're going to need to know what value of z cuts off 90% of the area, since we want to be 90% sure. So to find that, we're going to have to take a look at the standard normal curve, and we're going to have to find the critical values that cut off 90%. There's several ways to do this. You can just remember what it is because it's in the book. You can look in the table in the back of the book. You can use a TI-84 calculator. You can use Desmos. So let me show you a couple of ways that we might find this number. First, we can use the table in the back of the book. And you could certainly use the regular old standard normal table that we've looked at before, but there's a little insert, let's see, right here at the bottom of one of these pages. And it says, if I can get my camera to focus, 90%, right, would be cut off at 1.645. So that's the number that we need. Notice, from minus z sub c over to positive z sub c, we get 90% of the area, and the critical values that cut off that area are 1.645 and minus 1.645. Generally, when we're doing a confidence interval, we're either going to do a 90%, 95%, or 99%. So it's usually, or maybe 80%. Those are the four numbers that we generally use. So those are the most important ones. However, if you use a calculator or Desmos, it doesn't matter what percent you want, because the calculator is flexible enough to do all of them. And so on your TI-84, you're going to say, what the TIE4 only gives areas to the left. And so you're going to say, I want to know where, if I want a 90% confidence interval, I want 90% in between two values. That'll leave 5% below and 5% too high. So I want the Z distribution. Where is it? Okay, distribution. I want the Z that cuts off 97%. So I'm sorry, 90, it was a 90% confidence interval. So I want 95%. So I say 95, and it's going to say 1.645, just like the book did. Let me show you one more way. The last way, I'm going to share my screen with you. The last way, what's going on here? Here it is. Nope, here it is. Actually, I'll just share the whole thing with you. I think that's easier. Go over to Desmos. Put in your normal distribution. I can kind of remember how to type it because I've typed it enough times, but if you don't remember, go under distribution and put normal distribution in here. Okay, it's got a mean of 0 and a standard deviation of 1 because it's the standard normal. And we want the probability, right? We want the Z's that cut off an area of 90%. So we could just simply say minus Z, whoops, minus Z to Z. And then we could just calculate it something like this. We could just say, I'm just going to keep sliding this around. Let's go from 0 to 5. Here we go. Keep sliding this around until we get pretty close to 90%. Okay, so our Z would be about 1.65. And of course, here it is, shaded in. And if you want that, you know, to look a little nicer, you can sort of update, you know, fix the range here. 0 to 1 maybe. Okay, and then here's a little bit better picture of it. There's 90% of the area. Notice that if I just use a slider here, I don't get a very accurate number. So if I want the actual number from Desmos, I'm going to say, and this is a little complicated, so you'll have to maybe look it up if this is the method you choose, but we want to do the inverse CDF. Whoops, that's not where I wanted it though. Let's put it down here. The inverse CDF, okay, and then you have to tell it which distribution. And you'd say of a normal distribution with a mean of 0 and a standard deviation of 1 and an area of 90%. Oops, an area of 95%. Because when inverse finds it, it finds it to the left of the cutoff. So if 90% is in here, then 10% is left over. So 5% is here and 5% is here. So left of this value would be 95%. So there's your number. And then that one's really accurate. And of course, if you want some other value, you can put any values in here you want. But we generally use 90, 95, 99. Okay, that might be a good place to pause. Questions about any of that?
No.
Okay.
No.
Find Z sub C, right, which is 1.645. Okay, and that's going to have to be book, table, calculator, any one of those ways I showed you. And you don't have to use them all, but pick one, or just remember this number. That's the last way you can do it. All right, so that's the first step. The next step is to say, how far over would I be? So what I want to do is I want to calculate my margin of error, and my margin of error is plus or minus 1.645 standard deviations away, or Z sub C times sigma, right? we call this the standard error of the mean. So what would we get? We get 1.645 times the 1.5 over the square root of 20, which you could plug in because you already calculated it, right? I'm going to do it again so I have all my decimal points. So here we go. Drag it back on my screen and multiply it times 1.645. I get 0.55, maybe 17 something. I'm just going to round off to 0.55. Okay. So what that's telling me is that if I go up a half a year, a little over a half a year, and down a little over half a year, that would be a 90% confidence interval for my estimate. In other words, the mean, the true value, okay, is going to be a little less than our estimate plus the margin of error, and bigger than our estimate minus the margin of error. So to do that, we'd say the mean then is going to be between, is this 22.9? 22.9 plus the 0.55 and 22.9 minus the 0.55, which means our mean is between, again, I'm going to have to use a little calculator here. I got 22.9 plus 0.55, or 23.45, which I think I'll round up to 23.5, and down to 22.9 minus 0.55, or 22.4. Okay, so we can write the confidence interval using greater than, less than, like this, or we can write it in interval notation and say, my confidence interval is 22.4 up to 23.5, and we'd have a 90% confidence interval. Something like that. Basically what that says is, if I were to take samples, lots and lots of samples, 90% of those samples, right, would contain the true mean. In other words, the actual average age of college students would fall in this range. And that's what we call a confidence interval. So we report it a couple of ways. Sometimes on studies, like I was watching some coronavirus stuff on the TV the other day, and they were saying, the average recovery time is 15 days plus or minus 5 days. Okay. I was also looking at some polling data, and it said that 60% of the people approve of the way the president's handling this, plus or minus 4%. So sometimes we get the answer reported as 22.9 plus or minus the 0.055. So you can write your confidence interval either as an interval or as an estimate with a margin of error. And either one of those will work fine. You'll just have to figure out which one my stat lab is asking for and put it in the right way. Okay, that is a sample problem. If you want to look at it again, it's, what is it? I think I took it from the book so that you could look at it again. Where are these ages? That's student athletes. We did that one last time. I don't know where it is. These are the ones I did last time in the book. I thought I took it from the book. Oh, here it is. It's example number 5. It's example number 5 in your textbook. It's on page 303. So if you'd like to look at it in a little bit more detail, you can certainly go back and look at it right there. Okay, questions?
Nope, not at all.
None at all. You feeling okay about that? Section 6.1.
Yeah.
Good. Are you ready for 6.2?
Oh, yeah.
Okay. Here's the problem with this estimate. Sigma is known. Well, you're not going to know the spread of the population, right, without knowing the mean of the population. It seems like if you knew anything at all about the population, you'd know the average, right? And so this is an unlikely situation. And so what we need to deal with is what happens when we want to estimate the mean, but we don't know the spread of the population. And so that's where section 6.2 comes in. And it's going to be very similar, but we're going to have to account for more error, because instead of knowing this value, we're going to have to guess it. Okay, so let's, I need a piece of paper. Let's see if we can take a look at that. Okay, so we want to make an estimate when we don't know the standard deviation. So what we said in the first case was that the mean of our distribution of sample means is equal to the mean, and the standard deviation is equal to the standard deviation of the population divided by the square root of the sample size. And this gives us enough information then that we can build our confidence interval. The problem in 6.2 is we don't know this value. And so instead of using, this unknown value, we're going to estimate it. Right? Estimate sigma using, what do you think we're going to use to estimate it? We're going to estimate it using the standard deviation of our sample. I mean, since we don't know how spread out the population is, we're going to take a look at the sample that we collected, and we're going to say, we're going to estimate the mean using the mean of our sample, and we're going to estimate the spread of the population using the spread of our sample. Now, this creates a bit of a problem because we're already going to have some errors in our estimate because we estimated the mean using a sample mean. And now we're going to also create more error because we're going to estimate the spread of the population using the spread of the sample. And when that happens, we get more error, okay? And it turns out that let me write this down. When we take the mean, all right, minus our estimate, divided by the standard deviation, which we've estimated using the sample standard deviation, we don't get a normal curve. This curve isn't normally distributed. It turns out, so normally we would write Z here for a normal curve. It's not normally distributed. It actually has a little bit different shape. And if you go take mathematical statistics and keep taking more stat classes, we can kind of prove what shape it has. But it turns out that this has what we call a student T distribution. The good news is we know what distribution it has. The little bit bad news is that it's not a normal distribution. So we can't use the area under the normal curve to figure out what our critical values are, to figure out what our margin of error is. Instead, we're going to have to use the T distribution and find the area under the T distribution instead. So let me switch back over to Desmos, and I'll show you what a T distribution looks like. Share screen. This is just this will work. Okay, so you guys have Desmos back up now?
Yeah.
All right. So here's our normal distribution, right? And here's the finding some area under the normal distribution. There we go. I'll just put the normal distribution up there. It turns out that when we approximate the standard deviation using the sample standard deviation, we get a t-distribution, and we can graph it. And that's the beauty of Desmos. So I'll pop this up. I'm going to go down here to a new one. And of course, it has a nice mathematical formula. Remember, the mathematical formula for normal distribution was something kind of messy with an e to the minus x squared. This also has a mathematical formula, and I'm not too worried about it. I'm just going to graph it by its name for now. And if you want to look at the actual mathematical formula of the t-distribution, then you have to dig a little deeper in the book. So I'm going to pick t-distribution off of my list. And the t-distribution turns out to be a little more complicated than the normal distribution, because the t-distribution is going to, the shape of the curve is going to change based on the size of the sample. The way we say that in general for distributions is that it's got a number of degrees of freedom, and the degrees of freedom are going to, the shape of the curve is going to change with the number of degrees of freedom. It turns out that for us, the number of degrees of freedom that we will use is always going to be one less than the sample size. But let me just put it in here for, you know, any old degrees of freedom, which we'll call D, maybe. Usually in the book, it's going to call it DF, right, for degrees of freedom. Desmos doesn't like two variable names, so I'm just going to call it D. And I'm going to add a slider for it. And so check this out. When there we go. When D is 1, when there's 1 degree of freedom, we get this purple curve instead of the red one. So you'll notice the red is standard normal curve. But if we made a histogram of all the t-scores that we got when we did all the samples, we would end up with this purple curve instead if we were to estimate the standard deviation of the population using the standard deviation of the sample. There's more error, in other words. So check out what's happening. It's more spread out, right? It's further down here, there's more down here, and more area up here. It's more spread out. Still bell-shaped, still symmetric, and the area under the curve is still equal to 1, which makes it a probability density function, but it's more spread out. And the reason there's this additional spread is because we've introduced additional error by estimating the sample, estimating the population standard deviation using the sample one. However, there's kind of good news. As the degrees of freedom goes up, now that I'm at 2, now I'm at 4, let me go in integer values because it just seems reasonable that you wouldn't go by partial ones. You got to go kind of by whole degrees of freedom. Look what's happening as my degrees of freedom get bigger and bigger. The purple curve is starting to look more and more and more like the normal distribution. So by the time I get out to 50 degrees of freedom, they're almost the same. Essentially what this is saying is if we sample a great big sample, then it doesn't matter, right? We're going to get the same thing. If we sample a small sample though, then we're going to have to account for this additional spread because our areas are going to be quite a bit different between these two curves. Now, we can still find the cumulative, we can still calculate the cumulative probability. In other words, we can still calculate the area under the curve. And of course, from minus infinity to infinity, we still get 1. From say 0 to infinity on 1/2, we get half of it. And from -1 to 1, notice that we have only 60 instead of the 68 that we would expect with the normal curve. right? That's because there's more spread, so there's less area here in the middle. Okay, so the way this thing works out then, I'm gonna stop sharing. The way this thing works out is that if we want to estimate the population mean and use, instead of using sigma, estimate it with the sample standard deviation, then the whole calculation works the same, except we have to use the t-curve instead of the normal curve. So let me see if we can work through an example. In fact, I'm just going to find one from the book so that if you guys want to try it again on your own, you can always come back and look at the example in the book. Here's a good one. This is the coffee shop one. I'll just share it with you here in the book, and then we'll see if we can do it. Okay, so it's coffee shops. You're going to, you want to know what's the temperature of the coffee sold in the coffee shop. So since you all have to do lots of drive-throughs now because all the coffee shops are closed, you're going to be concerned that maybe, you know, when they hand the coffee out to you, it's like boiling hot and you take a sip and you drop it in your lap. And I don't know if you've ever done that, but exceedingly bad, right? You burn the top of your mouth. And so coffee shops are pretty concerned about this because they want it to be hot, because if they hand it to you and it's cold, then you get cold coffee in the drive-through, then you don't come back. But if you get coffee that's too hot in the drive-through and you take a sip of it and burn your mouth and drop it in your lap, then you don't come back. And so the average temperature of a cup of coffee is a big deal to drive through coffee shops. So here's what you do. You want to know what's the average temperature of coffee sold in coffee shops, right? And you have no idea. So you're going to try to estimate the average temperature of coffee using a sample. I don't know why my focus is bouncing all over the place, but I've just got a little tiny bit of shadow on it. And every time I move, it keeps refocusing. Sorry about that. We're on page 312 if you wanted to look in your book, so it's easier to look at. Okay, so we want to estimate the mean, and here's what we know. We're going to go to 16 coffee shops. We're going to buy a cup of coffee, measure the temperature, and then take all 16 of those numbers, add them up, divide by 16. And what we're going to get is 162 degrees, which seems pretty hot to me. I think my Keurig is set at 127, but maybe that's not true. I'll have to go check that again. But anyway, we get an average of 162. So we'd say, well, based on our sample of 16 shops, we think that the average cup of coffee is going to be about 162 degrees. And you'd say, well, hey, you know what? You only looked at 16 shops. There's thousands of coffee shops. How do we know you didn't just go to 16 that had really cold coffee or 16 that had really hot coffee, right? We would like to build a confidence interval so that we can say the average cup is 162 plus or minus, right? A little, how much? Well, in our sample, right, we can also calculate the sample standard deviation. So the sample standard deviation in the sample of 16 coffee shops that we collected was plus or minus 10 degrees. So you could say, well, I kind of think that the coffee in general would be like 162 plus or minus 10 degrees. And that would give us a pretty good idea. But we want to be sort of more precise and come up with an actual 95% confidence interval so that we can say, if we were to sample shop after shop after shop after shop, we could be 95% sure that our confidence interval would capture the true mean. In other words, that our estimate is pretty good. So let's see how we go about doing it. We're going to make an assumption here. We're going to make one assumption. And that assumption is that the temperatures of coffee, okay, from these shops are normally distributed, meaning it's all kind of mound shaped and symmetric. And the reason we need to do that is because we've only picked a sample size of size 16. If we pick a great big sample size, then of course the central limit theorem is going to tell us that the distribution of the sample means will be normally distributed. In this case, it's only kind of partially normally distributed because it's 16, right? But if we know that the population is normally distributed, then the distribution of sample means will turn out to be normally distributed as well. Okay, so let's do it. Here we go. Okay, so here's what we are going to do. We've got the distribution, right, of coffee temp. So these are the temperatures. This is for the whole population. We know that they're normally distributed, but we don't know what the average is. So we're trying to estimate this. Okay, so what do? We go and get a sample. And in our sample, right, in our sample, we get a sample mean of X bar, and we get a sample standard deviation of S. So this is sample N equals 16. So since we have these 16 numbers, we can add them up, divide by how many there are. Most of the time, the problem's going to do that for you and just tell you this number. So in our problem, this turned out to be, I've lost the problem, 162 degrees. And of course, we can find the sample standard deviation, take the difference from the mean, add them all up, right? Square them all, add them all up, divide by n-1, take the square root. So this is the formula back from chapter 2. And when we do that, we got 10 degrees. It's most likely, making sure, yeah, 10 degrees. So it's most likely though that you're gonna get, kind of some messy decimals. Okay, so be it, do it on the calculator. Now what we wanna look at is a third distribution. It's the distribution of all possible samples. It's the distribution of all the possible samples. And so we want to say, well, what does this look like? And the answer is, well, it's going to look mostly normally distributed, okay? It's going to look normally distributed like this with a mean of the sample means and a spread of the sample means. So we're going to say the mean of all the sample means is equal to the mean, and the spread of all the sample means is sigma over the square root of n. Notice that we have three distributions. The actual temperatures of all shops. We got the temperatures of the 16 shops that we actually took in our sample. And now this distribution is the distribution of all possible samples. So you take these 16 shops and those 16 shops and these 16 shops, right? And this would be the distribution of all the possible samples. The problem is that we don't know sigma. So what we're going to do is, instead of using sigma, we're going to use the standard deviation of our sample, S, to approximate this. And when we do, we're not going to get the standard normal curve. We're going to get, I wonder if I have a different color. We're going to get a curve that looks a little bit more like this. Okay, a student t distribution. It's going to be more spread out. Okay, and the mean right? The mean of our red distribution is going to be centered right here at the mean still. But the spread, okay, but the spread is going to be given by S over the square root of the sample size, because we're going to estimate the population standard deviation using the sample. Okay, so here's how we find our confidence interval. We need to first figure out how much confidence we want. It usually tells us in the problem. And in this problem, we wanted our confidence to be 95%. So we're going a confidence interval of 95%. Oops, let me slide up here a little bit. Okay, so we're going to have to figure out what, and now since this is a T curve, we need to figure out which T's or which critical values of T cut off 95%. So it's the same as we did for a normal curve, except now we're using the T curve and we need to know where 95% is. So here's what I'm going to do. I'm going to go back to Desmos. You can again use the back of the book or the calculator. I'm going to use Desmos to do it. We want from 1 to 1 cuts off 60%. We want what cuts off, right? What cuts off 95%. And in this case, the distribution had 3 degrees of freedom. And the curve we want is going to be 1 less than the sample size. So I'll write that down over here. The degrees of freedom is n minus 1. And our n in this case was 16. So we have 15 degrees of freedom. So instead of having a slider, I'm actually going to put the 15 in there. And you'll notice that the purple curve and the red curve are pretty close to the same, right? And if we want to do this the way we did it before, we can sort of slide the Z around until oops, 0 to 5. We can slide the Z around until we get 95%. So there's about 95%. Maybe I can go a little bit further over. There's 94.98. So that's pretty close to 95%. We would get a Z of 2.13. In other words, 2.13 is going to cut off 95% of the area. Okay, so if you want this number a little bit more accurately, we can say inverse CDF. In this case, our function was the T distribution with 15 degrees of freedom. And we need to cut off 95%. So we want to the left so that we've got 0.95%, right? Plus this 2.5% that's left over. So we end up with 2.13144. So there it is accurately. And again, you could look this up in the back of the book as well. So if we need 95%, we're going to put in 975 because that extra 2.5% would fill up this little tail on the left-hand side. Okay, so we found our critical value, T sub C. It's 2.13. Notice that what we're doing here is pretty close to the same as what we did for Z curves. The difference is that we're using this T curve instead. Okay, so we found our critical value. And now all we got to do is calculate a margin of error. So the error is going to be our critical value number of standard deviations away from the mean. In other words, it's going to be 2.13 times sigma was 10 over the square root of the sample size, which was the square root of 16. And then using a calculator, I'm going to get don't know what I'm going to get. I'm going to get, it looks like I'm going to get about 5.3. Okay, so we know that our average is going to be less than our sample mean plus the margin of error, which in this case is 162, right? Plus 5.3, or up to about 167.3. And it's going to be greater than our sample mean minus our margin of error, which turns out to be, I don't know what it turns out to be, 156.7. So if you want to write this down succinctly, you would say 156.7 over to 167.3. And then if you're reporting out your results, you're going to say the average cup of coffee, right, served by coffee shops is between 156.7 and 167.3 degrees, and I'm 95% sure. Okay, that's how you work this out. If you don't know the standard deviation of the population, you have to use the student T-curve instead. There's a bunch of problems in the book that you can take a look at. There's a few homework problems that you can start to take a look at. And of course, I'll be around here. I mean, we can ask questions right now. You can come back during office hours, or you can send me an email. How are we doing? That was pretty quick and a lot of stuff.
Pretty good.
Okay. Any questions?
Nope, got it.
Nope.
Okay. Well, our plan is to see if you guys can do a few of these problems now in 6.1 and 2, and try to, see how much progress we can make. I would like to talk about estimating proportions like next week, and then maybe wrap the whole thing up by maybe the end of next week. So we're going to be doing section 6.1, 2, and 3, and then that's it from chapter 6. And I'd like to see if we could shoot for maybe the end of next week to get it all done.
Okay.
Okay. So why don't you guys, good. All right. Well, why don't you guys try some problems, and then if you get stuck, you can come back during office hours or send me a note. One also asked if he could get a copy of this page. And the answer is, I think so. It's in the book, right? It's probably clear in the book on page, this example was on page 312. So this particular one was on page 312. And so you could look in the book. The other thing I'm going to do is I'm going to post a recording of what we talked about today. And so you can always go kind of scroll through the recording and get, and listen to it again if you want to listen to it again. But I will also, I can also probably take a picture of this and send it to you. What else can I help you with? Anything else? Okay. Well, then I'm going to take off. I'm going to go get myself a cup of coffee and do this again. So if you want to listen in again, you're welcome to. Remember that you guys are always welcome to come at 10 o'clock instead of the 8:30. It doesn't matter which class you sign into. And you're always welcome at office hours too. So if you don't have anything else, I'm going to let you go. You guys have a great weekend. And, please send me a note if you think that I'd be able to help you.
All right. Thank you so much.
Okay. You bet. Have a great weekend.
You too.
Thanks. I'm good.
One, before you, I lost one already. Okay.